In a series of both short and then longer videos, we're going to illustrate what this general stiffness method is all about by a progressive set of examples that build up our understanding. In essence, it's very much like the slope-deflection method because of a couple of reasons. One, the slope-deflection method really is just a specific example of a stiffness type of approach that follows the notion of identifying somehow degrees of freedom kinematically within a structure, having some sort of relationship between forces and displacements for what we call members in that model. We end up writing equilibrium equations where the unknowns are these unknown member end displacements, those kinematic degrees of freedom. And so we're solving the math for those, and then once we have those, we feed them back into the force displacement relationships to come up with member forces and then other response quantities that we may have of interest. So for a very simple kind of example of what this general stiffness method is all about, let's take a look at a two-span beam that has just a point load in it, and we've got this roller support in the middle. From a flexibility model perspective, we'd end up with 4 redundant reactions, one of them associated with the axial elongation or shortening of the member, so decoupled from everything else, but we still end up with 4 redundant reactions, from which then we're going to end up with, once we relax those 4 reactions, we'll have 4 primary displacements due to the actual applied load, and then 16 flexibility coefficients. These are all displacements associated with the unit values of the redundant reactions. And anytime any one of these little parameters about the members changes or the load changes, then potentially all 16 of those flexibility constants, some of those 4 primary displacements in the relaxed system might change, and then as well, depending on whether we know or whether we have the relationship for the prescribed displacements for those associated with those redundant reactions, those may or may not change too. But particularly these 20 displacements may change. The slope deflection approach here for this kind of system can look at this as purely a 1 degree of freedom system, that we have an unknown member end rotation right here at the roller support. So 1 kinematic degree of freedom, we write the slope deflection equation for both members, we get the fixed end moments associated with that load, which really means we create equivalent effects at the 2 ends of the member, and we solve for that 1 degree of freedom. In the general stiffness method, really we're doing the same thing. It's just when we eventually get into a numerical example with the general stiffness model, you'll see that how we come up with these stiffness coefficients is a little bit different. But this Q that you see here are equivalent nodal forces or force effects, moments, shear forces, axial forces. These are the unknown nodal displacements, and then again these are the stiffness coefficients. And even though we've pulled out the slope deflection model as though it's different than the general stiffness model, in reality we're still going to be solving the same kind of equation, and it's all about eventually how do we come up with what these stiffness coefficients are. That is the different approach, and we can generalize even this approach such that we'll have the axial elongations or shortenings included directly in this kind of approach, whereas in the slope deflection model we ignore those. So this is a step forward in terms of being truly more general, but that's not what the general really means. It means how we're going to go about getting those stiffness coefficients, and we'll begin to see that in the next couple of videos.